You ever stop and think about why the universe seems to run on waves? I mean, everything from light to sound, it's all waves. For a long time, we've had the math to describe them, but a brand new paper just dropped a bombshell, a shockingly simple reason for why they have to exist in the first place. So let's get into it.
Okay, so the big mystery really starts right here. You see, all these wildly different kinds of waves can all be broken down into the same fundamental building blocks. You know, sines and cosines. That's the whole idea behind Fourier analysis. It's like a universal alphabet for describing patterns. But here's the thing, just because you found the alphabet doesn't mean you understand why nature chose those specific letters to write with.
And that, right there, leads us to the core question of this whole explainer. Why this pattern? Is it just some happy mathematical accident? Or is there something deeper going on? Something that actually forces nature to use these wave-like building blocks over and over again? What makes them so, well, inevitable?
Now, the classic explanation, don't get me wrong, it's powerful. It's all wrapped up in heavy-duty calculus, things like orthogonality and projection integrals. And it gives us this incredibly precise toolkit for how to work with waves. But it doesn't really give you that satisfying gut-level aha moment. It's all mechanism, but no real reason. It explains the how, not the why.
But what if the answer isn't buried in all that complexity? What if it's actually hiding in a really simple geometric rule, something almost like a kid's game? This new perspective basically tosses out the complex analysis and starts from scratch with just one single elegant clue.
So here's our new game board. It's called the discrete slot. And really, it's just the space on a number line between two whole numbers. Let's call them A and C. Seriously, that's it. That is our entire playing field.
And here is the one and only rule of the game. If you want to fill that empty slot between A and C, you can only use one thing, its perfect exact midpoint, which we'll call B. As soon as B is in there, that slot is full. No other number gets to come in. It's a really simple, really rigid rule about perfect symmetry.
Okay, so this super simple rule, it has this huge, powerful consequence, which the paper calls a forcing principle. The geometry of the slot itself, it forces a single, unique outcome. There's no wiggle room, no other option, just one perfect fit.
Now, the formal name for this is the midpoint forcing lemma. All that really means is that the midpoint is the one and only point that's the exact same distance from both ends. It's perfectly symmetrical. That makes it the only admissible occupant. And just notice, we haven't touched calculus at all. This is just pure, simple geometry.
And this shows the difference perfectly, right? On the left, you've got the midpoint, totally balanced, totally symmetrical. Then on the right, you see that any other point is automatically asymmetrical. It's going to be closer to one side than the other. And in our little game, only perfection is allowed. That midpoint is special because there's only one of them.
All right, so we've got this one simple, really powerful rule. But what happens when we start scaling it up? I mean, how do we get from this one tiny little slot to the grand, complex patterns we see all across the universe?
Well, it happens in 4 really logical steps. First, a slot gets filled by its unique midpoint. Simple enough. 2, we start linking these filled slots together end to end, kind of like a chain. 3, as you keep building this chain of perfectly spaced points, a pattern starts to emerge. You guessed it, it's a wave. And 4, and this is so important, for the whole system to be stable and make sense, that chain absolutely must connect back to where it started, forming a complete closed loop.
Now, this idea of closure, the snake biting its own tail, is incredibly important. It's the geometric reason why Fourier series are considered complete, meaning they can represent pretty much any repeating signal you throw at them. It even explains a classic little quirk. You know how at a sharp corner or a jump, a Fourier series converges to the exact middle of the jump? Well, that's because that midpoint average is the one and only value that lets the loop close with perfect symmetry. It's amazing.
So we put all the pieces together. We started with a simple rule, built a chain, and closed the loop. It's time for the final reveal.
So here's the big takeaway, the whole point. The periodic waves that Fourier analysis is so good at describing, they aren't just some useful mathematical trick. They are a structural necessity. They are literally baked into the logic of space itself, forced into existence by this simple, undeniable geometric rule that any given space can only have one true center.
So let's just recap the key takeaways here. First, and most important, these periodic waves, they're not an accident, they're a structural necessity. Second, this whole idea is built on a simple geometric rule about midpoints, not a bunch of complicated math. You really don't need calculus to get the fundamental why. And finally, all those other concepts we talk about, like frequency and completeness, they just emerge naturally from how these geometric chains are spaced out and forced to close on themselves.
And honestly, it might go even deeper than that. The paper wraps up with this really provocative thought, suggesting that this simple geometric logic doesn't just explain waves. It might also explain other fundamental and sometimes pretty weird patterns that we see in physics. It's hinting that maybe other big secrets of the universe aren't hiding in some complex equation, but in simple structural rules like this one, just consequences of a universe that seems to demand symmetry. It makes you wonder, right? What other patterns are just sitting there waiting for us to find their simple, inevitable rule?